Welcome back to Physics 192. I'm Gerard Blanchard. Last time we introduced alternating voltage sources into our electrical circuits, and the consequence of introducing an alternating voltage source into an electric circuit is that you get an alternating current. The current in an alternating current circuit depends on the circuit elements that you have in the circuit. Most simply would be a resistor. Let's take a look at the current through a resistor in an alternating current circuit. The alternating current in a resistor is in phase with the voltage, and the maximum is given by I max, or the maximum current, is equal to delta V max, which is the maximum voltage across the resistor, divided by the resistance. Let's take a look at an example of that. Here I have a circuit that consists of a 5 volt, 500 hertz alternating current supply. Alternating voltage supply. That would be this element right here. You see it's a circle with a sine wave in it. That symbolizes an alternating voltage supply. And it is 5 volts, 500 hertz. And I have a 100 ohm resistor applied across the source. So we have a circuit here consisting of the source and the resistor. This probe shows where we are measuring the voltage and the current in the circuit. And I've grounded the circuit. I put my 0 volt point right here. Let's take a look at the graph of the voltage versus time. The top graph is a graph of voltage going from 0 up to 6 and down to -6 versus time in milliseconds. You can see here that the voltage is a sine wave. It rises to a maximum, a peak, and the peak is 5 volts. Then it decreases, goes back to 0, goes down to -5 volts, and then repeats, goes back up to 5, and so on. So the alternating voltage means that we have a voltage that changes as a sine wave from V max is equal to 5 volts to negative V max, which would be -5 volts. And the alternating is done by the sine term, sine of 2 pi times the frequency times time. And let's make some notes here. I will note that the frequency is equal to 500 hertz. And the time for one period is 2 milliseconds. So the period is equal to 2 milliseconds, or 2 times 10 to the -3 seconds. And so the frequency and the time should be related by the period of the oscillation is 1 over the frequency. Let's check that. The period is 1 over 500. And 1 over 500 is 1 over 500 is 2 times 10 to the -3 seconds. So 500 oscillations per second, or 500 hertz, is consistent with a period, or a time for a complete oscillation, of 2 times 10 to the -3 seconds. So remember that V is equal to, or delta V is equal to delta V max times the sine of 2 pi ft. So this term is what's giving us the alternation, the sine wave, and delta V max is 5 volts. And I'll write that down to delta V max is equal to 5 volts. So the maximum that the sine wave can be is +1. So the maximum that the voltage can be is delta V max times +1. So delta V max is the maximum voltage. 180 degrees later in the oscillation, we would have the minimum where sine is equal to -1, so delta V would be equal to -5 volts. So delta V oscillates between +5 and -5 volts, as we saw in the diagram. Now, let's take a look at the current through the resistor. There's only one current in this circuit, so I can measure it anywhere. I'll measure it at this point, and you can see that the current is also a sine wave. The current starts off from 0, rises up to a maximum, down, up, down, and so on. And the maximum current is 50 milliamperes. So I'll make a note of that. I max is equal to 50 milliamperes, or 50 times 10 to the -3 amperes. And the resistance is 100 ohms. So according to our equation, I max should be equal to delta V max divided by R. I max is 50 times 10 to the -3. Is that equal to delta V max, which is 5, divided by R, which is 100? And so we have 50 times 10 to the -3 is really 5 times 10 to the -2. And 5 over 100 is also 5 times 10 to the -2. So that checks out. So this equation describes what we see in our simulation. The maximum current is equal to the maximum voltage divided by the resistance. Let's take a look at those graphs a little more closely. Here we see that when the voltage is equal to 0, the current in the resistor is equal to 0. When the voltage is a maximum, the current in the resistor is also a maximum. Voltage is 0, current is 0, voltage is its minimum, and the current is equal to its minimum, and so on. Wherever we have a peak in the voltage, we have a peak in the current. Peak in the current, peak in the voltage, peak in the voltage, peak in the current. So the way that what we say is that the current and the voltage are in phase. They oscillate together. So what do we see here? We see that an alternating voltage is a sine wave between Vmax and negative Vmax. When we apply an alternating voltage to a resistor, we get a sine wave that is in phase with the voltage, so the peaks are lined up. And the maximum current is equal to the maximum voltage divided by the resistance. So we can see that that first equation is consistent with our diagrams. So we see that the current through a resistor and the voltage through a resistor for alternating voltage and alternating current is the same as what we've been using all along for direct current, namely that the voltage across a resistor is equal to the current times the resistance. When we add in inductors, however, and capacitors, things are a little different. The alternating current in an inductor is positive 90 degrees out of phase with the voltage, and the maximum current is given by I max is equal to delta V max divided by X sub L. X sub L is called the inductive reactance. So inductors don't have resistance, they have something called reactance, meaning that they react to the alternating voltage. The inductive reactance depends on the frequency of the alternating current and the inductance of the inductor itself. So X sub L is equal to 2 pi times the frequency times the inductance. So X sub L is equal to 2 pi FL. Let's take a look at that in our simulations. Here we see a circuit with an alternating voltage source and an inductor, specifically a 31.8 millihenry inductor. So this is the same voltage source, so it's 5 volts, 500 hertz. So it's 5 volts, 500 hertz. And now, let me add that in, the inductance is equal to 31.8 millihenries, or 31.8 times 10 to the minus 3 henries. And so what would we expect for the current through the inductor? Well, first let's calculate the inductive reactance. X sub L is equal to 2 pi f L. The inductive reactance is 2 times pi times the frequency, which is 500, times L, which is 31.8, times 10 to the minus 3 henries, or the inductive reactance is equal to 2 times pi times the frequency, 500, times the inductance, 31.8, times 10 to the minus 3, and I get 100 basic metric units of inductive reactance. I didn't mention this before, but the basic metric unit of reactance is also the ohm, just like resistance. Reactance is not resistance, but they appear in the equations the same way, so they have to have the same units. So the inductive reactance is 100 ohms. So then I max is equal to delta V max divided by the inductive reactance, or I max is equal to 5 volts divided by 100 ohms, or I max is equal to 0.05 amperes, which is 50, that is 5/100ths of an ampere, which is 50,000ths of an ampere, or 50 milliamperes. So I'll go ahead and do that conversion for you. That would be 1,000 milliamperes in 1 ampere. And if you work that out, you would get 50 milliamperes. The amperes cancel out, and 0.05 times 1,000 is 50. We're left with milliamperes. So we're expecting to see a current of about 50 milliamperes. Let's go back to our simulation. Here we have our current, the current through the inductor. This is 40 milliamperes, and it's slightly higher than that, so we'll call that good. The even more interesting thing to see here is that the current through the inductor is not in phase with the current from the power source, from the alternating voltage source. The voltage peaks on this line at 0.5 milliseconds, and the inductance peaks not at that time, but 1/4 of a cycle later. One full cycle is 1, 2, 3, 4 of these lines. That is a full cycle, and up, down, up. The current through the inductor peaks 1 tick mark later, or 1/4 of an oscillation later. So that is 90 degrees. So the current through the inductor is 90 degrees after the peak in the voltage. So we would call that we would say that the current through the inductor is out of phase by the voltage by plus 90 degrees, 90 degrees later. And so also interestingly, we can see that we get the maximum current through the inductor at the same time as the voltage supplied is zero. So we're not talking about resistance. For resistance, the current and the voltage are in phase. Max lines up with max and zero lines up with zero. For an inductor, the max current lines up with zero voltage. So you can see here we have zero, peak, whereas here we have peaks where the voltage is zero. So the current through the inductor is 90 degrees out of phase, plus 90 degrees out of phase with the current, with the voltage from the voltage source. So what do we see here? We see that an alternating voltage alternates like a sine wave. We also saw that the current in a resistor is in phase with the alternating voltage, while the current through an inductor is 90 degrees out of phase with the voltage. What if we have both a resistor and an inductor? If we have both an inductor and a resistor, then we call that an LR circuit. L for inductor, R for resistor. And the alternating current in an LR circuit is phi degrees out of phase with the voltage. And the maximum current is given by I max is equal to delta V max divided by Z, where Z is the impedance. Impedance is a combination of the resistance and the reactance, and the impedance, Z, is given by the square root of the resistance squared plus the inductance, the inductive reactance squared. So that would actually be something like Pythagoras' theorem. Z squared is equal to R squared plus XL squared, or Z is equal to the square root of R squared plus X sub L squared. And the angle phi is equal to the inverse tangent of the inductive reactance divided by the resistance. Now, these equations should seem familiar from when we were working with vectors. And in fact, we solve alternating current questions using phasors, not vectors, but phasors. Let's take a look at what I mean by that. So here we have an LR circuit with an alternating voltage supply. The alternating voltage supply has a maximum voltage of delta V max. We have a resistor in series with an inductor. The voltage across the resistor is delta V max is equal to I max times the resistance. The maximum voltage across the inductor is delta V max is equal to I max times X sub L. We're going to represent this circuit using a phasor diagram, as you can see here. Along the x-axis, we have the current phasor, I max. I max we will line up with the x-axis. The voltage across the resistor is in phase with the current, so we will also put the voltage across the resistor along the x-axis. So we have our phasor delta V max is equal to I max times R, also along the x-axis. The voltage across the inductor is 90 degrees out of phase with the current, so we're going to place that on the positive y-axis. So the voltage across the inductor is represented by a phasor at 90 degrees to the x-axis, or along the positive y-axis. So delta V max is equal to I max times XL, represents the phasor of the voltage across the inductor. Now we add those two voltages together just like vectors. We add those two voltage phasors just like we do vectors. So delta V max across the entire circuit is the hypotenuse, as you can see here. And the angle between delta V max and the current is phi, as you see here. So now we can use our trigonometry to solve for the relationships between delta V max and I max. Pythagoras' theorem tells us that the hypotenuse squared, or delta V max squared, is equal to the sum of the square of the sides, or I max r squared, I max times R quantity squared, plus I max times the inductive reactance squared. We have, in both of those terms, we have an I squared. Once we square, we have an I squared, so I'm going to factor that out. That tells me that delta V max squared is equal to I max squared times the quantity R squared plus X sub L squared. Solving for I max squared, we have delta V max squared divided by the quantity R squared plus X sub L squared. And then taking the square root of both sides, we have the relationship I max is equal to delta V max divided by the square root of R squared plus X sub L squared. So that denominator, the square root of R squared plus X sub L squared, is the impedance. So that's where the equation for the impedance comes from. The impedance of a circuit is equal to the square root of R squared plus X sub L squared. And that's what appears in the denominator for the relationship I max is equal to delta V max over Z. So impedance also has units of ohms, as you can tell by the equation for impedance. Finally, to get the angle phi, we can take the inverse tangent of the opposite side of the triangle divided by the adjacent side of the triangle. That would be the inverse tangent of I max times X sub L divided by I max sub R. And the I max is the same in the numerator and the denominator. We divide that out. And then we're left with the equation, the angle between the voltage and the current is equal to the inverse tangent of X sub L divided by R. Let's take a look at that in our simulation. Here we have a circuit comprising an alternating voltage source, a resistor, and an inductor in series. The resistor is a 100 ohm resistor. Given that the inductor is a 31.8 millihenry inductor and the frequency is 500 hertz, we already calculated that this inductor would have a reactance of 100 ohms at that frequency. So we have a 100 ohm resistor and we have a inductor that has a reactance of 100 ohms at 500 hertz. And so what do the voltage and the current look like? Here's the voltage, looks like our sine wave as usual. The current, however, is now neither in phase. The voltage is peaking at this line right here. So if the voltage were if the current were in phase with the voltage, it would peak on this line, which it doesn't. If it were 90 degrees out of phase, it would peak on this line, but it doesn't. So the current is somewhere between 0 and 90 degrees out of phase with the voltage. And in fact, it peaks pretty much right in the middle. So we could estimate that the current is something around 45 degrees out of phase with the voltage. And we also see that we have slightly less than 40 milliamperes of current through the circuit. Let's check all of that out. So once again, we have delta V max is equal to 5 volts. The frequency is 500 hertz. And R is equal to 100 ohms. And L is equal to 31.8 times 10 to the minus 3 henries, which tells us that X sub L, which is equal to 2 times pi times F times L, would be 2 times pi times 500 times 31.8 times 10 to the minus 3. So I said that that should come out to be 100. That was my intention. Let's see, 2 times pi times 500 times 31.8 times 10 to the minus 3 is in fact 100 ohms. So the inductive reactance is also 100 ohms. The impedance, Z, is now equal to the square root of R squared plus X sub L squared, or Z is equal to the square root of 100 squared plus 100 squared, or the impedance, Z, is equal to the square root of 100 squared plus 100 squared, and that is 141 ohms. Just like in reactance and resistance, impedance also has basic metric units of ohms. So our impedance is 141 ohms. So what is Imax? Imax is equal to delta V max over Z, or Imax is equal to 5 over 141, 141, not 144, 141. So Imax is equal to 5 divided by 141, 5 volts divided by 141 ohms, and that would be 0.035 amperes. So once again, times 1,000 milliamperes per ampere. So Imax is equal to 35 milliamperes. And that was what we saw in our simulation. And finally, we have phi is equal to the inverse tangent of the inductive reactance over the resistance. Phi is equal to the inverse tangent of 100 divided by 100. 100 over 100. And that is going to be the inverse tangent of 1. Inverse tangent of 1 is 45 degrees. So as we saw, the current is 45 degrees out of phase with the voltage. So all of our calculations agree with our simulation. So our calculations of the maximum current and the phase angle between the voltage and the current agree with what we saw in our simulation. Now, let's work an exercise so that you can get some practice at working with alternating current LR circuits. A series combination of a 22 millihenry inductor and a 145 ohm resistor are connected across the output terminals of an AC generator with a maximum voltage of 120 kilovolts. At a frequency of 1250 hertz, what are the voltage amplitudes across the inductor and across the resistor? And then a question, do the voltage amplitudes add to give the source voltage? i.e., does delta V max across the resistor plus delta V max across the inductor equal 120 kilovolts? Let's draw our diagram. Here's our alternating voltage source, and we were told that it's 1.2 kilovolts, so that would be 1,200 volts. And the frequency, so that'd be delta V max. And the frequency was 1,250 hertz. And we have a resistor and an inductor connected in series. The resistance is equal to 145 ohms, and the inductance is equal to 22 millihenries, or 22 times 10 to the minus 3 henries. Let's go ahead and calculate the reactance. X sub L is equal to 2 pi FL, or X sub L is 2 times pi times the frequency of 1,250 hertz times the inductance of 22 times 10 to the minus 3 henries. So the inductive reactance is 2 times pi times 1,250 times 22 times 10 to the minus 3. That gives us 173 ohms. I forgot my ohms up here as well. So the inductive reactance is 173 ohms. Let's calculate the impedance of this circuit. Z is equal to the square root of R squared plus X sub L squared. So the impedance would be the square root of 145 squared plus 173 squared. So the impedance is square root of 145 squared plus 173 squared. And that gives us 226 ohms of impedance. Okay, what were we asked for? We were asked for the voltage amplitudes across the inductor and across the resistor. Well, delta V max across the resistor, or I should say that the current in the circuit is equal to delta V max across the resistor divided by R. And we can solve that for delta V max across the resistor, and that would be delta V max across the resistor is equal to I max times R. And we have a similar thing for the inductor. I max across the inductor is equal to delta V max across the inductor, or divided by the inductive reactance. So delta V max across the inductor is equal to I max in the circuit times X sub L. So we know the resistance, we know the reactance. So if we knew the current in the circuit, then we could calculate delta V max across the inductor and delta V max across the resistor. Now this is a series circuit, so there's only one current, one value for the current. The maximum current, will say the positive direction is this way and then the negative direction is that way. That doesn't really matter, except that I've just drawn that little arrow. But the point is that whatever current goes through this wire has to go through both of these and through the power source. So there's only one value for the current at any time. We can calculate I max for the circuit from the voltage of the voltage source and the impedance using I max is equal to delta V max of the source divided by the impedance, or I max is equal to 1,200 divided by the impedance of 226 ohms. So I max is equal to 1,200 volts divided by 226 ohms of impedance, or 5.31 amperes. So that is the maximum current in the circuit. What is the voltage across the resistor now? That would be I max times the resistance, and the voltage across the inductor would be I max times the reactance. So let's calculate those two. Delta V max across the resistor is equal to I max times the resistance. So delta V max R is equal to 5.31 times 145, or delta V max R is equal to 5.31 times 145. That would be 770 volts. While the voltage across the inductor, delta V max L, is equal to I max times X sub L, or the inductive reactance. So delta V max L is equal to the current, same current, 5.31, times the inductive reactance of 173 ohms. So delta V max L is equal to 5.31 times 173, which gives us 919 volts. So the peak voltage across the resistor is 770 volts. The peak voltage across the inductor is 919 volts. Do those add up to the peak voltage from the voltage source of 1200 volts? Well, let's see. 770 volts plus 919 volts give us 770 plus 919 give us 1,689 volts. So if we just add the two voltages together, then we get more than the voltage across the power supply. The power supply was 1,200 volts, but here, if we add these two together, we get 1,689 volts. Well, so that doesn't add up. What if we used our phasor diagram and added up these two voltages as phasors, as a triangle? Well, let's see. On the x-axis, I'll put delta V max R is equal to 770 volts. And on the y-axis, I'll put delta V max L is equal to 919 volts. And then let's see what the hypotenuse is. delta V max is equal to, well, it's going to be equal to the square root of 919 squared plus 770 squared. So the square root of 919 squared plus 770 squared equals what? Square root of 919 squared plus 770 squared gives us 1,199 volts, which will round off to 1,200 volts to have three significant figures. So the hypotenuse is 1,200 volts, and the hypotenuse is the voltage source supply, is the voltage, the maximum voltage of the voltage source. So the voltage across the resistor adds to the voltage across the inductor like phasors. Not as numbers, but as phasors or vectors, because the voltage across the resistor and the voltage across the inductor are 90 degrees out of phase with one another. When we add them up as phasors, however, we get the proper voltage across the power supply. So remember that when we're dealing with LR circuits, we should treat them as phasors, which are similar to vectors, with the voltage across the resistor being 90 degrees out of phase with the voltage across the inductor, and the voltage across the resistor being in phase with the current. So, when we're working with LR circuits, with the circuits that consist of an inductor and a resistor and an alternating current, then the current through the inductor is 90 degrees out of phase with the voltage. The current through the resistor is in phase with its voltage. And we add up the voltage across the resistor and the voltage across the inductor similarly to vectors. In fact, we call them phasors instead of vectors, phasors. And the voltage of the voltage source powering this circuit is the hypotenuse of the phasor diagram. We're going to work more examples of LR circuits, and we're going to add in capacitors next time. Until then, think physics.